Hey everyone, so we're going to continue on with chapter 12, and ultimately we're just going to finish it because it's talking about center of gravity, which you did really awesome on the conceptual problems today, and then still doing a couple more examples with static equilibrium, kind of like very similar to the seesaw problem that we did earlier. Now, center of gravity is very, very similar to center of mass. And we kind of think about center of gravity and center of mass. We know one is just with mass versus one, gravity is more of a force. So we can kind of consider mass versus weight, similar concept of our mass versus center of gravity. So it says that the torque due to gravitational force on an object of mass m is the force mg. So we already know that. That's just the weight force that's acting at the center of gravity of the object. So center of gravity is just where all of the mass is aligned with the acceleration due to gravity. And for us, usually it coincides with the center of mass because we typically assume, or we like to think, that G is uniform over the entire object. And in most cases it is. So if acceleration due to gravity is uniform, so it's the same over the entire object, then center of gravity and center of mass will be at the exact same place. If the object is homogeneous and it's also symmetrical, the center of gravity will just coincide with the geometric center of that particular object. Okay, so let's say that it's not symmetrical and we have more of an extended particle, kind of like what we have here. An object can then be divided into very small particles, and each particle we know will have its own mass and it will have its own specific coordinate. And we have talked about that before with center of mass, and we find that by taking the sum of the masses times their distance then from specifically that center of mass over the total mass. And this is just the x component form. We can also say a similar expression for the y component. But that's what center of mass is. So how does center of gravity deviate from that? Well, center of gravity is just now going to include the acceleration due to gravity for all of those particular particles that we're summing up. So now I have the total mass is going to be, if I take the masses of all of the particles times then their distance away then from that center of gravity point times their acceleration due to gravity, then that should give me my center of gravity. But if all of the g's are just the same, then ultimately g ends up canceling out. So if g is uniform amongst the object, then I'm just left with center of mass. So center of mass and center of gravity will always coincide as long as g is uniform. And for us, like I said, in most cases they will be. So again, if I sum up all of my particles and take their x components and multiply them by the masses, so I'm going to take the mass of this one times x1, but now I'm also going to take it times g1, or that acceleration due to gravity. I'm going to take mass of m2, multiply it by the x component here, x2, multiply it by the acceleration due to gravity. I'm going to add that to the third particle, x component times mass, and also multiply it by the acceleration due to gravity. If I want to find then the center of gravity of that object, all of the particles summed up should give me the center of gravity. So the mass of the total mass, which we just symbolize here as a capital M, times the gravitational acceleration, times in the x component of where that center of gravity is located. So if the acceleration due to gravity is 9.8 here and it's 9.8 over here, it wouldn't matter. Acceleration due to gravity just tells me then that would be canceled out in my equation up here. So then that means I'm just left with the center of mass. So that's how we can show center of mass and center of gravity are the same. Okay, so let's go back and look at another example of static equilibrium. And remember that we said that for static equilibrium to hold true, we want the net external torque that's acting on the object as well as the net external forces acting on the object to equal 0. And remember we said there's a difference between static equilibrium and dynamic equilibrium, and that static equilibrium signifies that something is at rest, and dynamic equilibrium is signifying that something is moving with a constant speed or constant velocity. So, ladder example. A uniform ladder of length L rests against a smooth vertical wall. It says the mass of the ladder will symbolize with just a lowercase m, and the coefficient of static friction between the ladder and the ground is 0.4. I want to find the minimum angle theta at which the ladder does not slip. So first things first.
Interruption. We have at least 2 cars that need to be moved. They're in the flood zone, and the parking lot is backing up. One is a burgundy Toyota.
Sorry, guys.
Parked close in the visitors area, right next to the sign that says this is a flood zone. Also a blue Toyota Corolla. The water is approaching your door jamb. So we got to move those cars immediately. Any other car that is close to the building in the visitor spot, it may be recommended that you move to be safe. Thank you.
Okay, so we want to find the minimum angle theta at which the ladder does not slip. So just some problem-solving strategies to kind of help us out. I would first say, let's draw a sketch and decide what's in the system, what's outside of the system. Well, ultimately, we know that we're going to be able to do that by drawing some type of free body diagram. Let's draw a sketch of the ladder, which really we already were given that here. So let's draw a free body diagram. Let's talk about all of the forces that are acting on the object. I want to label all of those forces. I want to indicate the locations of all of those forces. Let's establish a coordinate system. Let's look if there's components of them. We're doing all of that by just drawing our free body diagram. And then we can think about net force or net torque and still follow our signs of X and Y direction. So that's our first strategy. So by doing that, that's what I've done here. Here's my ladder of length L. I have the normal force of the ground acting up, pushing up on the ladder down below when it's on the ground. And I also have friction. The ladder could move this way. Friction is going to move in the opposite direction. So that static friction here is what's keeping it from slipping. And remember that theta is still right here. The ladder itself has a center of gravity because it has a weight. So it's going to have a weight force. So I know that it says it's a uniform ladder. I'm assuming that this is a uniform ladder. So if it's uniform, the center of mass is just going to be directly in the middle. So the center of gravity or that weight force is going to go directly down. Now, this is leaning up against a smooth vertical wall. Smooth vertical wall here. So the wall is going to exert a normal force out this direction on the ladder, and I've symbolized that with the symbol P. So these are all of our forces that are acting. Now, some of these forces, though, if I think about P and if I think about the weight force, this is not going to be the vector that's going to be applying some amount of torque, or is going to be same thing that will go for this P. And I want us to break these up into component form. So I've drawn this on the board. And this is how I would break it up looking at it into component form. Remember that something that applies a torque has to be perpendicular to what we call the lever arm, which would just be really the radius. And in this case, that's my ladder. So I want to think about the forces that are acting perpendicularly to that ladder. The weight force is just straight down. It is not perpendicular to the ladder. So if I break that up into components, then I can see then that that circled component, the Y component there, is what's going to be the force that's going to create some type of torque. If I look up at P, where I called that, remember, I symbolized that was the normal force that the wall is pushing up on the ladder. So in that particular instance, I see that it's a component of P that's going to be responsible for causing some type of rotation for the ladder. So this diagram that I had in your notes, we need to include those component pieces because it's really, really important that we understand that the lever arm and the force have to be perpendicular with one another. And that's not shown here on this picture. So I just want to make sure that we get that and that's cleared up. Okay, so let's just say I'm thinking about just forces alone. I'm not talking about torque yet. We're just going to talk and look at forces. So the sum of the forces in the x direction. Well, I have friction, and then I have my normal force here that's from the wall. And since I want this to be at rest, I'm going to say that they have to be balanced, so that's equal to 0. So this vector and friction have to be equal to 0. Sum of the forces in the y direction. Normal force here, the ground pushing up on the ladder, and then I have the weight force of the ladder itself, and those should be equal to 0, so normal minus mg equals 0. That means the normal equals mg, and I also know then, ultimately, we just took this and just simplified it even more by saying that I know that friction is equal to mu times the normal, but we also just said that the normal was equal to mg. So that means that P has to equal mu sub s times mg. Okay, in the next kind of problem-solving strategy, we've kind of talked about, we wrote out our forces using Newton's second law. I want to think about the exact same thing in terms of a net external torque now that's happening. So in this case, again, we want torque to be balanced. So I want to know at what angle the ladder will not slip. That means that my rotation of axis is going to be right here at what I just called that 0 for the origin. So will the normal, or will this frictional force that the ground is exerting on the ladder, will either of these forces provide some type of torque? No. And that's because their radius would just be 0. So they will apply no amount of torque in terms of, or any type of rotation on this ladder. So that's why I have here the sum of the torque is equal to, for the normal, the torque that could be provided for this friction, the torque that could be applied for the center of gravity for the weight of the ladder, and then the torque that can be applied from the wall that's pushing on the ladder. So these two are 0. That's where I got my 0 for these two. But now I have the torque due to the center of gravity. Now, I know that torque is simply force times the radius. So, or the cross product of torque times force times radius. So, oh guys, I switched these. I'm just kidding. So let's go here to this one. This one is really for this one, and this was for this one. I'm sorry. So, but let's still stick with the center of gravity for the ladder. So here's my center of gravity, and I know that it was the component. If the ladder is this way, the force has to be acting perpendicularly to that ladder. So like we showed on that picture before, I want the y component of this particular triangle, and then theta would be right there. So it would be mg cosine theta, but it's mg, and remember I want my force, so there's mg cosine theta, but torque is force times the radius. And in this particular case, if this is my axis of rotation here, from the origin to where the center of gravity is, that's going to be half of the length. Yes, please. It's going to be half of the length of the ladder. So that's where I got the L over 2. Okay, so this is the torque for the center of gravity. Now, the last one that I need to think about is the torque that's for this normal force that's being produced from the wall. So in this case, I know the force we've symbolized as P, but this force is not perpendicular to the ladder itself. So remember, we drew a triangle, and my y component would be here, x component would be here. So if my y component is here, my theta would be right here. I get P, and that would be sine theta. So P sine theta would be my force, And then I want to also multiply that by the radius, the lever arm, to get my torque. And from the origin up to the top of the ladder where P is located, that radius would be the length of the ladder, that would be L. So that's how I got these two. And I'm setting that equal to 0 because this ladder needs to be, I don't want the ladder to slip. So ultimately, just doing all of this math here, I can say that P L sine theta equals mg L over 2 cosine theta. If I can get, ultimately I rearranged all of this to where I could get sine theta over cosine theta, because we know sine theta over cosine theta is just tan theta. And then when I did that and I rearranged that, ultimately on the right hand side I got mg over 2p. Well, we said from the forces that p was the same thing as mu times mg. That's what we did from a couple slides ago. So I just subbed in that right here. Well, look here, masses cancel, g's cancel, so I'm left with tan theta equals 1 over 2 times mu. The only thing that we were given was mu, and that was 0.4. And I was asked to find the minimum angle at which this ladder won't slip. So I have that value. I want to find this. So I've eliminated all of the variables that I didn't have to begin with, and using the variable that I do have, so that way I can find theta. So ultimately, if we plug all of that in, theta should give us 51 degrees. Okay, the last example that I want to look at is the horizontal beam example, because it's very, very similar to the last one. So a uniform horizontal beam with a length of L of 8 meters and a weight of 200 newtons is attached to a wall by a pin connection. Its far end is supported by a cable that makes an angle phi of 53 degrees, and that's with the beam. A person, got a little construction worker guy here, his weight is 600 newtons, and he stands a distance 2 meters away from the wall here. I want to first find the tension in the cable, as well as the magnitude and direction of the force exerted by the wall on the beam. So let's first find tension here. That's our first goal. Second goal, find the magnitude and direction of the force exerted by the wall on the beam. Okay, so that means the wall is going to apply some normal force on this beam. So kind of use the same ideas as what we were using from the first one. We know the beam is uniform, so I know that the beam is going to have a weight, and I already know that that weight was 200 newtons, and so that 200 newtons is going to be placed directly in the geometric center of the beam. I know that the person is standing on the beam. I want to know the tension. So here's my weight force for the person. Here's my weight force for the beam. I have tension that's going to be directed upward this way, but I also have the beam, or the wall, exerting some type of normal force on the beam. And this force is going to be directed this way. The overall vector is going to be directed this way. Why? Because it needs to somehow balance the vector here for tension. So this force here is just the force that's exerted by the wall on this beam. So I just simplified this down. I called that normal force that's exerted by the wall onto the beam R. The tension here is T. I know that this was where the person was standing, so the person here is 600 newtons. They gave us that. And then the center of gravity for the beam was 200 newtons. And then I have my angle here, 53 degrees. So here's our free body diagram. We're using the, I'm going to say that the pivot point will be here at the wall, because it's just usually easier. What we don't know is tension, which I need to know. And then I also need to know magnitude of this, and then theta, because they asked me for the direction of that as well. Okay, so next I want to break all of my things up into components. Why? Because remember we said that torque has to occur when the force is perpendicular to the lever arm. So in this case, my r sine theta is going to be perpendicular, my t sine of 53 is going to be perpendicular. And here we just added, if this was 0, from the wall to where the person was standing was 2 meters, from the wall to where the center of mass is just 4 meters. So let's plug everything in, set everything up so that way we can solve for what we need to solve for. Okay, so if we first, we can solve for tension first, or I could, ultimately we want to solve for tension. I know that torque that's going to happen on this particular ladder, or this particular beam, sorry, not a ladder, beam. I know torque is equal to the force times the radius, force times the lever arm. Well, I know that this isn't going to be able to apply that while exerting a force on the beam because my R would be 0. So what I do have applying a force, or applying some torque to this beam, is going to be the weight of the person. The beam itself is going to apply some amount of torque based on this axis of rotation here. And then the tension in the cable will also apply some amount of torque. So I have, let's just start here with the tension. So I know that this is the component that's perpendicular to my lever arm. So I use T sine phi, which that's just the 53 degrees, times then my length of the lever arm. If this is my axis of rotation, then remember the length of the beam was 8 meters. So I know that the length here, it's going to go from here to here. That's 8 meters. So I get T sine phi L. That would be the torque that's applied for the tension. I also know that the person is going to be able to apply some torque. So I'm going to take the weight of the person times in that 2 meters here. So I just called that D. And then I have the weight of the beam itself is going to be the weight of the beam, which is 200 newtons, times half of the length, because it's only halfway to from the origin to where that center of mass is, that center of gravity is. So that's why I have weight of the beam times L over 2. So we already know all of these numbers, so I plug them in here to solve and rearrange here to solve for tension, and I get tension to be 313 newtons. So we have figured out tension, but now my goal is to figure out what is this R, what is my vector of R, how much force is the wall applying or exerting on the beam. So I broke down my X and my Y components in terms of forces. I know that the force in the X direction is R cosine theta, and that would be minus T cosine 53, or T cosine phi, but we already know that phi is 53, and that should be balanced, so it should equal 0. So really just R cosine theta is equal to T cosine theta. I did the same thing in the Y direction. I have R sine theta in the positive direction, T sine of 53 or T sine phi in the positive direction. I'm subtracting that from the weight of the person and also from the weight of the beam. Those should all be balanced as well. That should be equal to 0. So what I did, I took these two equations and I set R cosine theta equal to then T cosine theta, and then I set R sine theta equal to the rest of this. So the weight of the person plus the weight of the beam minus T sine phi, and I divided them by each other. Why did I do that? I did that because ultimately I can get R to cancel out, and sine theta over cosine theta is tangent theta. And I know what this is. I know the weight of the person. I know the weight of the beam. We just solved for what tension was, and I also know what phi is. That was 53 degrees. So I could figure out what theta is, and that's 71.7 degrees. Well, if I know the direction of R, then I could find the magnitude of R, because ultimately I know I could just plug in for one of these X components up here that we've already written for to solve then for R. So in that case I used just the X because it was a lot easier. And when we do that, we get R to be equal to 581 newtons. Okay, so that's the last example that I have for the static equilibrium. Your homework problems are going to be very similar to these. We are going to work on these book problems in class some tomorrow. Again, your practice test is up on Monday in class. We can ask questions on the practice test, on homework problems. We'll solidify concepts. Tuesday will be your test over chapter 11 and 12. So I hope you have a really great night, and I will see you tomorrow. Bye.